All right, so welcome to chapter 3. So in this chapter, it's the second law of thermodynamics, or we're finally step into the one of the heart of thermodynamics, or key concept in thermodynamics, which is entropy. So before talking about entropy, we want to use today's lecture to first introduce you to what are the terms of second law of thermodynamics. It's going to be very long and jargon-like, but this is going to be a quick introduction. But later on, after we finish everything, discussion of entropy, we'll come back and revisit our second law of thermodynamics and see if we understand a little bit more about the nature of energy, heat, work, what's the difference between them, etc. Now today we'll be focusing on, first introduction on the first law of thermodynamics, and then we'll spend a lot of time talking about heat engine, or in the other way, like what is a heat engine, what is a reversible heat engine, how do we construct a Carnot cycle, and what kind of information we can get from the Carnot cycle. So, getting started. First, the second law of thermodynamics. So these statements were coming directly from your chapter textbook, and we'll just read it together. Right? We have different statements for the second law of thermodynamics. They're all very long and jargon-like, but we can read it together. In the Kelvin-Planck statement of the second law of thermodynamics, what we have is that it is impossible for a system to undergo a cyclic process whose sole effects are the flow of heat into the system from a heat reservoir and the performance of an equivalent amount of work by the system on the surroundings. Super long. Like if we translate it a little bit, what we want to say is that a cyclic machine or any kind of machine cannot completely convert the random molecular energy of heat, right? If you think about temperature change and also heat transfer. So when we're having heat transfer, the nature of those heat transfer are the random molecular energy. And the nature of work that's being done, like PV work we were mentioning, right? It's a kind of mechanical work resulting in volume change. Now that is the ordered motion of mechanical work. So the Kelvin-Planck statement of the second law of thermodynamics basically say, hey, a cyclic machine can never 100% transfer heat into work. That's the second law. We have a different version of the second law of thermodynamics, which is a Clausius statement. It says it is impossible for a system to undergo a cyclic process whose sole effects are the flow of heat into the system from a cold reservoir and the flow of an equal amount of heat out of the system into a hot reservoir. So that means not only we cannot transfer heat 100% into work, we cannot build a cycle. Basically, it's like hot to cold and then cold to hot in 100% efficiency. I know that's what I feel like when I read these statements. I'm like, what exactly are we talking about? So let's look at some example and also what exactly is the heat engine. And then later on, we'll see how are we going to use the second law of thermodynamics to get something that's quite intuitive to us. All right, getting started. First of all, what is a heat engine? So in a heat engine, what we are saying is imagine we have a hot reservoir, like something at a higher temperature, TH, and then a cold reservoir at a lower temperature, TC. Now, a heat engine is something in the middle. The heat engine absorbs heat from the hot reservoir. So this QH is a positive number, because if we focus on our heat engine as our system, right? So heat flow from the hot reservoir into my system. So my QH is a positive number. And part of that QH flowed into the system will be transferred into the cold reservoir. So that's why my QC is a negative number. So that's emission of heat from the heat engine to the cold reservoir. And hence, heat is flow out from the heat engine, and then this is a negative number. But in between, the heat engine will transfer some of the QH into work. All right, so the heat engine is absorbing heat from the hot reservoir and output work to the surrounding. So that's the work done by the heat engine to the surrounding, and hence my QH is positive, QC is negative, and also my work output is also a negative number. All right, so that's basically telling us what is a heat engine. Now, within the heat engine, what we care about is how much work we can get out from the heat engine, given we know what QH and QC are, or just knowing what QH is. So that leads us to define the term as efficiency. So we define the efficiency of a heat engine as the amount of work output per cycle. So in this case, the work output is a negative number, but we want the efficiency to be a positive number. So typically we take the absolute value of the work, which is like negative output, right? So we take the absolute value of the work that's being output from the heat engine to the surrounding, dividing that by the total amount of heat flow into the heat engine. So that gives us the efficiency of my heat engine. With me so far? Right, so we went over what is a heat engine, how does the heat engine do, and now we define the efficiency, which is something we care about. Now, one more thing, like what else do we know about the system? Remember, we learned our first law of thermodynamics. So combine the first law of thermodynamics, we can get more information about the heat engine and also the efficiency. So imagine now we are using our first law. And we hope to set up this engine. Like right now, we're just showing like half of the cycle of my heat engine. You can easily imagine this to, we can close it to be a cyclic process so that you can have another like engine that's like a refrigerator that's absorbing work from the surrounding and then heating up the temperature and pump the cold reservoir energy to the hot reservoir energy. So like another one to close it to become a cyclic process. All right, so this is like halfway. We have the hot reservoir, hot temperature. You have a heat engine that absorbs heat from the hot reservoir. And that heat engine do work to the system, to the surrounding. Now imagine we have another part that goes back. We have like a refrigerator, right? So this refrigerator basically is, we have some kind of work that's doing, the work go in the refrigerator. And then we're pumping energy into the hot reservoir and then doing the same, absorbing heat from the cold reservoir. So the reverse version of this. So the heat engine would output work, right? And a refrigerator will be, the surrounding do work on the refrigerator, and we're pumping energy from the cold reservoir to the hot reservoir. All right, so that's a cyclic process. Imagine this kind of a cyclic process. Now we have a cyclic process. We have a first law of thermodynamics. We have more information we can use. So in this kind of cyclic process, we have delta U equals to Q plus W. And delta U of my cyclic process is, want to take a guess? For a cyclic process, what is the change of my internal? Yes, that's 0, right? So we have that equals to 0. So in this case, we're moving the terms to get that W equals to QH plus QC. Right, that's just using the first law of thermodynamics and define a cyclic process. And now divide both terms with QH. And that becomes negative WQH equals to 1 plus QC over QH. And in here, our left term, this one is our efficiency. So our efficiency is 1 plus QC over QH. So what does this information tell us? So in any kind of cyclic system, whenever we're dealing with QC and QH, it doesn't matter what magnitude they are. They always have the different sign, right? We're always either inputting energy from the cold reservoir to the hot or hot to the cold. So they will always have a different sign. So that gives us information that the efficiency of any cyclic engine will always be smaller than 1. So we can never have an engine that's 100% efficiency, meaning transfer all the heat into work. So that's efficiency. That's a definition of efficiency, and what do we know about it? Let's take it one more step to look at Carnot principle. So, Carnot principle tells us the maximum amount of work from a given supply of heat is obtained with a reversible engine. So we're trying to prove the Carnot's principle. So in here, what we're doing is using the second law of thermodynamics, trying to prove the Carnot's principle. Now, when doing that, we want to do it, I'm going to go this like very slowly. If you feel lost at any step, just raise your hand and we'll go over it, all right? So in this case, for this proof, let's first go over the setup, right? So on the left-hand side, we have a reversible heat engine, basically acting as a heat pump, the same kind of setup we're doing. So this reversible heat pump would absorb heat, and then this reversible heat pump would be absorbing heat from the cold reservoir and the heat transfer into the hot reservoir, and there's something doing work on it. So that's the kind of refrigerator I was talking about. So again, what we have is we have W reversible as a input. So the surroundings, some kind of things, is doing work on my heat pump or my reversible heat pump. It absorbs heat from the cold reservoir, I call it QC REV. It transfers heat to the hot reservoir, I call it the negative QH REV. All right, so in this process, if we're only looking at the reversible heat engine as a heat pump, basically what's going to happen is the cold reservoir is going to get colder and colder, the hot reservoir is going to get hotter and hotter, if this is the only thing that's happening. But at the same time, let's imagine, because remember what we're trying to prove is that the reversible heat engine is the most efficient one. Right? So in order to prove that there exists a different kind of heat engine that is more efficient than my reversible engine, we manually set to say, like, what if there exists a super engine? And when say this is a super engine, we say that the efficiency of this super engine is larger than the efficiency of my reversible engine. And what does the super engine do? The super engine, it absorbs heat from the hot reservoir, and then the rest of the heat go to the cold reservoir, and there is a net work output. All right, so in this process, we can manually set to say my QH reservoir and the QH reversible and the QH super is the same. So that means the left heat engine or the heat pump is like giving energy into the hot reservoir at the same rate as my super engine pull heat from the hot reservoir. Or let's say the absolute value of this QH reversible is set to be equal to the absolute value of the QH super. Is this color working for you? Okay. And that's something we can manually control, right? Or just control, like, for example, if they have like different size, you just run at different times. But nevertheless, we'll manually set the absolute value of my QH reversible equals to my QH super. And what do we know? Now, this next part is to think about, we have the definition of our efficiency. So my definition of my efficiency, say like efficiency equals to the absolute value of work over QH. So given that we set E super larger than E reversible, so this is a hypothetical situation we set up, right? So the super engine is more efficient than my reversible engine. Thus the work, the absolute value of the work super must be larger than the absolute value of the work reversible. With me so far? So that leaves us to this one, right? We have a net work output for this hypothetical cycle if there exists an engine that is more efficient than a reversible engine. All right. And now we want to use our second law of thermodynamics. So I'm going to read that to you again, since you don't have that with you. Remember, in our first statement, the Kevin Planck statement of our second law of thermodynamics, it says a cyclic machine cannot completely convert the random molecular energy of heat flow into ordered motion of mechanical work. Right, so in our case, we have the cyclic machine. What we are doing in this hypothetical cyclic machine is having a hypothetical super engine that's more efficient than a reversible engine. And the whole outcome of the cyclic machine is some kind of net work output. And we derive that by only using the definition of efficiency and the hypothesis that the efficiency of a super engine is larger than the efficiency of a reversible engine. And this machine violates the second law of thermodynamics, and thus this machine cannot exist. All right, so it is not our role to prove laws of thermodynamics are true, but the purpose of this class is how to use these laws of thermodynamics and why do we actually care about it? What kind of information we can get from these laws of thermodynamics. So what we prove in this case is only using the second law of thermodynamics to prove that the most efficient heat engine or heat pump is a reversible heat engine or heat pump. Yes?
Can you go over one more time why the fact that there's the network output violates the second law?
Well, so let me go back to the second law and we'll read it again, right? So what is that? A cyclic machine cannot completely convert the random molecular energy of heat flow into ordered motion of mechanical work. All right, so take-home message, cannot completely convert random molecular heat flow into ordered motion of mechanical work. So look at the cycle we created. The only thing that's happening are these 4 heat flow, and we somehow got a net work output. And the fact we have a net work output violates the second law of thermodynamics. Because by only circulating energy, we're not supposed to get any net work output flow. Yes?
So like normal engines aren't the circle, since that would be impossible, right?
Well, so the whole point here is we're saying the reversible heat engine is the most efficient one. That's the Carnot principle. And that's what we're trying to prove. You can have other engine, but as long we can work on the efficiency of other engine. But what we're trying to prove here is that a reversible engine is the most efficient one. Yes.
Don't systems like this kind of already exist though?
It will exist, but you can't have the left one being a reversible engine and the other one being the more efficient one than the reversible. That's the point. Like, I mean, if both of them are non-reversible, then of course it exists, right? And if like one of them is irreversible, the other is reversible, well, we can have the energy flow from the reversible engine to the irreversible engine. What we cannot have is now we have a reversible engine, and it doesn't exist a super engine. So that's our take-home message. Or the other way to put it is this assumption violates the second law.
And that's because there's always going to be.
Because of the network output coming from the cyclic
Does
machine.
that mean like just waste work done on the system or done onto the surroundings?
I guess the way to put it is that in the second law, what we're saying is we can't transfer all, if the only thing happening is the heat flow, which is like not ordered heat flow. We cannot completely transfer those heat flow into ordered mechanical work. Okay, that's going to relate to something we will define later on as entropy. Yes.
What is a reversible heat engine?
So reversible heat engine basically say, again, reversibility tells you only very small steps can take place. So you can reverse the direction of that engine. Or for anything that's a reversible, if we think about the steps at the reversible, of a reversible engine, you can think about every step to be reversible, like infinitesimal changes only. But now let's take it one more step further to look at the Carnot cycle, because we went over the reversible engine being the most efficient one. So naturally, we want to know more about a reversible cyclic process. So in the Carnot cycle, we'll define this Carnot cycle with 4 different steps. Imagine we have a hot reservoir and a cold reservoir. And we have 4 different steps taking place. I'm going to first go over what exactly are these 4 steps. And then on the board together, we will work out how to plot the Carnot cycle on a PV diagram using the first law of thermodynamics and the things we already know. So in this case, we're looking at Carnot cycle for ideal gas. What do we have? Let's call our first step here. And the first step is a isothermal expansion. So we start from this point, a random point, and the gas will undergo a isothermal expansion. And then once it's expanded at the same temperature, TH, it will undergo an adiabatic process of cooling down. So even if it is adiabatic, we're seeing the temperature drop to a lower temperature of TC. And then this TC, well, the gas will undergo an isothermal compression to get back to a different temperature. So let's actually draw it on the board. It might be easier. So what we're saying is we want to have a diagram So this is our typical PV diagram. So on the y-axis, that's pressure. On the x-axis, that's our volume. So in our initial state, we're saying we start from our first point, which is at some higher temperature, TH. All right? And then the first step, we're saying the gas undergo an isothermal expansion. So it is an expansion, and also the temperature remains the same. What that tells us is we have a larger volume, but we want the temperature to remain the same. So how will pressure change? Now we know like volume will increase, but my temperature is the same, so my pressure is gonna decrease. So we'll have it somewhere here. That's our second point. And that's also at TH. All right, so this process is an isothermal process. The next question comes, then we want a reversible adiabatic process that's linking TH and TC. So where is gonna be my third point? So 2 to 3, we say this is a reversible adiabatic process. So in here, what do we have? We have different ways to solve it. Again, you can use the equation we derived last time or something more intuitive. So in here, we say this is adiabatic. So Q equals to 0. My delta U equals to work reversible. Right, so with the ideal gas law, we know that my internal energy is only a function of temperature. So what that means is at point 3, we're talking about this one have a lower temperature Tc. So what we have is UTH is larger than UTC. And in this process, what we're seeing is both of them will be negative. All right, just because the temperature is dropping, so at a lower temperature, the internal energy also decreases. And since we're looking at an adiabatic process, then my change of internal energy equals to the work reversible, means like the system is doing work on my surrounding, right? So my work reversible equals to negative PdV integral out. So in here, this one is negative, the work reversible is negative, we have a negative here, so my dV must be a positive number. So that tells us we have our point C somewhere here. TC, that's our straight. So these lines don't necessarily need to be straight. In my lecture notes, I make them straight because it looks prettier, but in fact, they are not straight. And as you look at the icon for our boiler, that picture is actually a Carnot cycle picture. And then from point C to our point 4, again, we have an isothermal process. But now we're talking about an isothermal compression with the volume decrease. The temperature remains the same, and my pressure needs to go up. Right. And then we want to find an adiabatic way to link my point 1 and point 4. Yes.
Why would the volume for the between step 2 and 3 get slightly bigger?
Well, that's what we're deriving here. So in this case, we find out that delta U must be a negative number because the temperature is lower and we look at ideal gas. All right, so delta U is lower, and at the same time it is adiabatic, means we find an adiabatic path linking these 2 points, my Q equals to 0, delta U equals to W reversible. Right, then W reversible equals to negative PdV. Since this one is negative, here we have another negative, my dV must be a positive value. I'll pause here for any questions you might have because it's important to get a good understanding about what is a Carnot cycle. And again, in here, we're looking at Carnot cycle, and for any Carnot cycle, every step must be reversible. And then my Carnot cycle involves two different isotherms. So these two are isothermal processes, or on my PV diagram, what we say is these lines are isotherm paths linking these two dots. And then we have two adiabatic paths when the temperature drops. Any questions before we move on? Okay. I have a more detailed walkthrough on the annotated notes if you want to check that out. And again, it's a very nice practice to look at every step and see if you can calculate, again, heat, work, delta U for every step, assuming an ideal gas. Nevertheless, so now thinking about what we did before, which is defining efficiency. And we went over our proof saying a reversible engine or reversible cyclic process is the most efficient engine. So naturally, we care about what is the efficiency of a reversible cycle like a Carnot cycle. So before we do that, we want to claim one thing, that the efficiency of any reversible engine working between different temperature is the same. And we'll go over that derivation and see why this claim is true. Or the other way to put it, the efficiency of a reversible engine is going to be a function of the temperature of the hot reservoir and the temperature of the cold reservoir, TH and TC here. And then we'll do the derivation to see why it is true, what exactly is that function for our Carnot cycle with ideal gas. Might be different if we're looking at a different reversible cycle, but for Carnot cycle and ideal gas, we can derive this function out. And I'm going to do that on the board, but I will give you some information here. So we have the first law of thermodynamics. We have our reversible PV work. I have something we know about perfect gases. All right. So from all these information, what we can get? Well, let's just write out our first law of thermodynamics, du equals to dq plus dw. Right, so looking in there, we know that for ideal gas, my du equals to cv dt equals to dq minus, well, this minus comes from the negative PdV, and this negative PdV is the negative nRT, well, nRT over V dV. So I can just write it as CV dt equals to dq minus nRT over v dv. All right. And then we want to move terms with terms so we can do the integral of the cycle, because right now we have t on the right-hand side, we have dt on the left-hand side. So we're just dividing both sides by temperature. And then my left side becomes CV dt over t equals to dq over t minus nRV dv. That's just using our first law of thermodynamics. And now imagine we do the integral on all three terms. But since we're looking at a cyclic process, so remember we have 1, 2, 3, 4 steps, but it is a cyclic process, right? So we can take the integral of the entire cycle. So that means a cyclic integral. Let's fix an integral over the entire cycle. We have CV dt over t equals to integral of dq over t minus nRV dv. Right, so whatever this term tells you is like this one as a sum of 4 different integrals. So basically this equals to the t1 to t2 CV over t dt plus t2 to t3 CV over t dt plus t3 to t4 CV over t dt and, well, t4 to t1 CVT over t. So that's just what that this symbol means. One more thing, like in math, basically, if we only have ordinary definite integrals, or the way to put it is if, can you see that in the back? Okay, so if we only have a function of x, dx, and this cyclic integral will go to 0. So that means if we only have a function of x and we're taking the cyclic integral of that function dx, this cyclic integral will vanish. So this is called the ordinary definite integral. All right. So what do we have here? Only using the math of the setup. On the left, this is a function. I mean, your heat capacity is a constant for ideal gas, but even for non-ideal gas, it is only a function of temperature, right? So my CV over T term will always vanish to be 0. My NR over V, dV term, will always vanish to be 0. Even for non-ideal gases, you can always write this one as a, you can always take that temperature out from the equation of state and write this term. So this one will always vanish. But nevertheless, what do we have here? We end up having this term, dq over t. This one, if we take the cyclic integral of the term dq over t, this term always goes to 0 for my Carnot cycle. With me so far? We'll come back to, in our Friday lecture to talk about the nature of this term dq over t. But remember what we discussed before. What is a thermodynamic state function? So a state function means for any initial and final state or for any cyclic process, that state function will vanish, right? So the change of that state function will vanish. I'm not saying the state function will vanish. So the change of that state function will vanish. So that tells us that my dq over t, or more specifically, since we're looking at Carnot cycle, all steps are reversible. We're saying this dq rev over t is a state function. All right, and we'll talk about what exactly is dq over t or dq reversible over t in our next lecture. But for now, let's work on our efficiency question. It went a little bit too far, but now let's come back to our question about the efficiency of the Carnot cycle. So this term, we can write it out, like what exactly are inside the cyclic integral. We have the integral between 1 to 2, and then dq over t plus 2 to 3 dq over t plus 3 to 4 dq over t plus 4 to 1 dq over t. Let me remove these for now. But we know some of the dq in these processes. Going back to our setup of our Carnot cycle, my 2 to 3 is adiabatic. My 4 to 1 is also adiabatic. So in here, this 4 to 1 is 0 because of adiabatic process is inconsiderate. My 2 to 3 is 0 because it is a adiabatic process. All right, so that's just the setup of my Carnot cycle. And between my step 1 to 2, my temperature is kept the same. It's an isothermal process. The temperature between point 1 to 2 is always TH. So you can write TH in. Between 1 to 2, we have dq over TH. And between 3 to 4, that's dq over TC. And these two integral adds up to be 0. Yes.
You mentioned dq over t is a state function?
Yes.
I thought q, it's not just the difference, it's like the process.
dq reversible over t is a state function.
Okay.
It doesn't mean q is a state function.
Okay.
All right, so remember, when we say q is a line integral, means we don't know what it is if we do not know the path. But if we already define the path to be a reversible cyclic process, now dq over t, this is a state function. We haven't talked about what exactly is that dq over t. We'll save that for the rest of the lecture, for the rest of chapter 3. But for now, in this process, what we have is, well, the dq over th plus the dq over tc adds up to be 0. Or effectively, in this case, because th and tc, these two are just constant, right? It's just a number. We can take it out from the integral, and that becomes 1 over th, integral between 1 to 2 dq plus 1 over tc, 3 to 4 dq. And then this integral is just, well, it's just an integral. You can just do that calculation. And we call this process QH. And the reason we call it QH, because that's a heat transfer happening for an isothermal process that takes place at a high temperature H. Likewise, the right one becomes 1 over Tc QC. Now, if we move, since these two terms add up to be 0, let's move the terms so that my Q go with Q and my C go with, my T go with T, Q go with Q. So what we have, let me move here. So we have QH over TH plus QC over TC equals to 0. We can rewrite that as QC over QH equals to negative of TC over TH. All right, this is just rewrite the terms. And in our definition of the efficiency of a heat engine, and remember the efficiency of a cyclic engine is E equals to 1 plus QC over QH. So we did that derivation earlier today. Imagine we have a cyclic engine. We use our first law of thermodynamics to get this expression here. Now we have a relationship of QC over QH, and this efficiency thus becomes 1 minus TC over TH for Carnot cycle, and also perfect gas. So now I'll give you one quick question to think about. Imagine we have a Carnot cycle. Say the efficiency is 40% at room temperature, which is 298 Kelvin. We want to improve the efficiency of that Carnot cycle. Which direction should we go? Should we spend effort to increase the temperature of my hot reservoir, or spend time to decrease the temperature of my cold reservoir? Now we have the expression here. Let's say this E is 40% at 298 Kelvin. Raise your hand if you think we should raise up the temperature of the hot reservoir. Raise your hand if you think we should decrease the temperature of the cold reservoir. All right, so there's a little difference, but the whole point here, you feel like you don't have any information, but we know information here. In this case, the TC, like the process of lowering the temperature, we can't go lower than 0. Right? It is just not impossible for us to go lower than 0K. But for our TH, it's more straightforward if we want to increase that temperature between 298 into 5,000. So that's something we can do on planet Earth. And that's easier if we want to raise the temperature to get a more efficient. Yes?
Would 298 be TH or TC?
That's just the problem given. I'm just saying the efficiency is 298 Kelvin, let's say 298 and 268. Which one do you want to alternate and make it more efficient? But nevertheless, that's just a quick introduction. So today, we went pretty fast. We went over our definition of second law of thermodynamics. We tried to use those second law of thermodynamics. The way we did it is to use our second law of thermodynamics to demonstrate the Carnot principle is true. Then we introduced the Carnot cycle, which involves 2 isothermal processes, 2 adiabatic processes, everything reversible. Then focusing on ideal gas, we derived the efficiency of the Carnot cycle. All right. And in my lecture notes, I have some sample problems in the textbook. So these are more let's say plug-in number kind of question, but it's nice to just practice and get familiar in these kind of questions. And by the way, we have our midterm next Friday, so we still have a few lectures before that. Next Monday, I'll give you a whole announcement on what to expect on our first midterm exam and how to best study for it. But just stay tuned, right? We still have a few lectures to go. All right, and good luck studying. Welcome to chapter 3.